All right, welcome back, everybody. So we'll continue, and it's the second lecture by Raul today. So he was very gracious. He actually proposed, in addition to his lectures, to have a special discussion session today in the evening. He'll say a few words about the plan this evening for you before the lecture starts. The floor is yours.
Yeah. First, how's everybody doing? People okay? Staying awake? Fantastic. So yeah, today, so I do, some of you already know, I do a lot of work on related to outreach, trying to like make our field as welcoming, as diverse and as impactful as possible. And so I figured we would have tonight a little bit of discussion about that. So I'm gonna have like a little bit of guided discussion, and I'll have some set of discussion points for you guys to have on your own. And so that's what we're going to do tonight. We're going to talk about diversity and outreach, et cetera, et cetera. So it's going to be a little bit different, okay? But I hope to make it, I promise not to make it too painful, okay? So please do come. I'll try to make it interesting and engaging and fun, okay? Let's see if I achieve that. Okay, so or does anybody have any questions about that? Does anybody have any questions about anything? Oh, fantastic. So why don't we pick things up from where we left off yesterday? I remember everybody was falling in love with Lattice. You were telling me you wanted to become Lattice QC practitioners. And so let's pick things up there. So we have this beautiful outline of things that we're going to cover. The last thing that we were trying to discuss is what can it be used for? And then the next question is what its limitations. So they're kind of correlated, but I decided to separate it in my brain. So what I was trying to convey to you is that spectroscopy of stable particles is relatively easy conceptually. Computationally, it costs time, money to do, but conceptually it's quite easy. And many states have already been studied, including ones that are not super stable. So, the pion, the kaon, the K star, the eta, eta prime, et cetera, including baryons and the heavy sector. Many states have been studied, confirmed with experiments, even some predictions have been made. And so the field is super robust and exciting. But, what more can we do? And the maybe take-home message that I was trying to give you yesterday is that QCD and Lattice QC is kind of like a match made in heaven, because the theory is perturbative in the UV sector. And so Lattice artifacts, we expect them to be small. But also we have dynamical mass generation, which means that the theory is short range. And so we can put it into a tiny little box and get away with murder. And so there's an assured mass gap. And so that means that we can non-perturbatively study QC properties, at least for some time, independent observables, in a straightforward way, for some set of states. Okay, so I'm kind of putting a lot of caveats here, but we can do quite a bit of physics. And so what are the limitations? The limitations are unclear. It's not really clear what we can do. There's, basically, if you tell me there's something we can't do, somebody's going to work really hard to prove you wrong. Okay, and that's what's happened multiple times. For example, PDS, for a long time, people said that it was impossible, it couldn't be done, and you've seen calculations, so it can be done. So the challenge is there's many things that are naively impossible that have been done, and really, it requires novel ideas that allows you to connect the observables that can be obtained on the lattice, which are observables defined in finite discretized Euclidean spacetime, to those that are of physical interest. Experimentalists, they don't know how to do calculation measurements in this world. Experimentalists only know about infinite volumes that are continuous and that are in Minkowski spacetime, right? And so in general, we can construct formalisms that are either perturbative or non-perturbative that allows us to map these kinds of observables. And I've been working quite a bit on developing formalisms that give us non-perturbative relations between these, and that's what I'll talk about for a good chunk of the rest of today. So limitations, it's not really clear. People are making proposals for doing quantum computing because it's real time, et cetera, and there's some benefit to that, but there's really no obvious limitations of what we can do with Lattice QCD and Euclidean spacetime. So I keep saying, here it says tomorrow, but tomorrow is today. So this is what I'll cover for the rest of today. I'll give you like a little taste of how you would do hadron structure. I'll just give you the simplest example. I'll give you also the simplest example of fundamental symmetries, and I'll dive into scattering theory because that's my bread and butter. So electroweak form factors, this is something that calculation has done quite a bit of work in trying to constrain. And this is basically where, lattice QCD really has made quite a bit of money. So you can imagine that what we can do is evaluate matrix elements of time-independent operators. So this is very tiny font, I apologize. But here I'm showing you, for example, the pi plus, going to the pi plus with an electromagnetic current sandwich in between, or the vector current. This can be related to a form factor up to kinematic pieces. And the key point is that this matrix element, this allows us to get form factors, and this matrix element is time independent. So you insert a t equals 0, and so you can calculate it using Minkowski or Euclidean, you'll get exactly the same answer. And so you can access these kinds of matrix elements from what are so-called 3-point correlation functions, where you put, say, a source associated with a pion at some point in time, let's say the origin, you put the current that you want at some intermediate time, and then you put an annihilation operator at some later time, okay? And so you let this, you calculate these things as, evaluating correlation functions that are statistically sampled, that you average over your gauge configurations, and you get this function. Then you can use the spectral decomposition, so insert a complete set of states, and after a little bit of massaging, you will get that this correlation function at very large times, where t is large compared to 0, and this delta t is large compared to t, you will have a matrix element that is, you will have this term, which is basically the matrix element of the vacuum to your single pion, sandwich with your interpolating operator for your pion. Same thing on here, where you have the vacuum to the pion. And then in the middle, you have the desired matrix element that you're after of the pion, current, evaluated at t0, and then your pion. And all the time dependencies and exponentials which depend on the spectrum, which you necessarily have to have constrained to be able to do this calculation in the first place. So you first get the spectrum, then you can evaluate these things, and you can then tease out this matrix element. And we can argue, using the same kind of arguments that I made yesterday, that this matrix element now it's no longer Minkowski or Euclidean because it's time independent. But more importantly, if the box is sufficiently large to fit the pion, so m pi l is large, of a marker. So the one parameter that dictates the size of all hadrons basically is the pion mass. And so if this thing is sufficiently large, then this thing would be exponentially close to the infinite volume matrix element. Okay. And so basically this is the gist of how all electroweak matrix elements have been calculated to this point, as long as the current is local in time, okay? And so the contractions that you would have to evaluate are something like this. So are there any questions about that? It's kind of fast, that's a lot of words. Super clear. Fantastic. And so this is what actual data looks like. For some, world where the pions are super heavy, but all the data basically looks more or less the same with more or less noise, depending on how good your statistics and your quark masses are. But you look at here, with delta t is a time separation of the is a time for the sink. The source is being evaluated at t equals 0. And you're scanning for different values of t, which is where you're inserting the current. And so for a small delta t, here's 12 in some lattice units, you will get something that doesn't quite look like a flat thing, where we've removed we've removed the exponential, so everything else is contamination. So you're seeing here that the contaminations are large. You make the separation a little bit bigger, it's starting to flat out. And then you make it a lot bigger, and you see like there's a region where this is relatively flat, you do some fits, and that's your quarter matrix element for that given value of the kinematics, right? Because you have some momentum for the initial state, some momentum for the final state. Then you vary this for different virtualities, different types of times, you do a global fit, yada, 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 and you end up getting constraints, kinematic constraints of the form factor. In this case, there's only one form factor because the current is conserved. And so the form factor must be equal to 1 at the q squared equals 0, because it's supposed to be the charge of the current. And then, it drops off and you can do a global fit if you want. That's the gist of how you evaluate these kinds of metrics elements. More complicated operators will require something more complicated, but the idea is basically the same. One calculation that has gotten quite a bit of attention is G-2. This has been so the anomalous magnetic moment of the muon. It has been quite interesting for a while because there was tension between experiment and theory. And then lattice was basically called to duty. This happened something in the order of 10 years ago, where the lattice community started driving into calculating the QCD contributions of the anomalous magnetic moment of the muon. Basically, what we have to evaluate is the coupling of the muon to a photon. And among the different contributions that are inside of here, there's the first leading order hadronic contribution comes from the hadron vacuum polarization of the photon exchange diagram here. So basically what you want to evaluate are the QCD contributions to the photon. And this can be calculated by evaluating correlation functions, where basically you're creating, so you can evaluate this by evaluating correlation functions with the vector current, which has the same quantum numbers of the photon. So you can evaluate currents that are separated in time. Here is honest to God Euclidean, so it took a little bit of time to prove this, that you can evaluate these kinds of correlation functions where you have some current at zero time, some current at later time, you average over all positions, then this gives you a correlator in time, and the hadronic contribution can be it's just equal to this function, this correlator that has been integrated over all times with some kinematic factor that can be evaluated analytically. And this has been a driving force of many different lattice calculations. And here's some data for different contributions of this diagram, where you have the light piece. So basically, we just only have light quarks. Then you have the strange piece as a function of time, and then the charm piece. So this is both the correlator as well as the kernel in units of the inverse of the muon mass. And so at the end of the day, you just have to grab this data and do a numerical integral of this data. And this has been how people have determined the anomalous magnetic, the QCD contribution to hadronic vacuum polarization, to the vacuum polarization of the photon, which is contributing to the anomalous magnetic moment. And basically, right now, lattice QCD has kind of washed away that tension with experimental determination, suggesting that perhaps there's no good new physics. So we'll see. There's still more calculations to be done, but it might be that there's no signal for new physics here. But this is one of the many examples where lattice QCD has really had impacts in trying to constrain BSM phenomenology. Okay, so these are just some examples. I figured the rest I'll talk about scattering, since that's what's part of my motivation yesterday. Do people have any questions at this point? You guys are extra quiet today. Yeah.
The last page, I think you are trying to calculate vacuum polarization in that diagram, and the Q square for that virtual photon can be time-like, I think. I mean the virtual photon that connected with this black block.
Yeah. So the claim is so what you can show is that this contribution can be this whole contribution can be written in terms of a correlator, which is this, and a kernel that is something that you can determine analytically. And so in this region, because you're scanning, basically, you're scanning regions where basically it takes a little bit of time to prove, but basically what you're scanning is kinematics, where let's say this is a momentum that is flowing through here. You're scanning kinematics where no intermediate hadron can go on shell. And that's important. So it's kinematics where you can't have, for example, the first possible singularity, and you'll see partly why and what I'll talk about. The first possible singularity that is infrared is due to intermediate pions going on shell. So the virtualities that you're scanning here are such that these intermediate particles cannot go on shell. And so two things happen. One, the finite volume effects are exponentially small. So that is equal to the infinite volume analog. But also the time sensitive effects are irrelevant. So the Fourier transform of a Minkowski correlation function and the Laplace transform of a Euclidean one are equal to each other. And so that's what's made this calculation possible. Yeah. Yeah, great question. Anything else? Going once, going twice. Sold to the quietest bidder. Okay, let's go into scattering. So let me start by saying there's two minimum criteria for doing scattering on the lattice. One is going with a single operator, this like simple technology that has allowed us to do many determinations of single particle states, which actually is being, let me finish the sentence and I'll correct it. So the simple technology for studying single particle states just fails miserably for studying multi-particle phenomena. That's the correct statement. Now let me make a second one. If we want to do precision physics for single particle states, what has been done historically of using a single operator is also not enough. So let me tell you why. Let's say that I wanted to study something simple, like the rho on the lattice. The rho is unstable. It decays 100% of the time to 2 pions. And so let me try to construct a basis of operators that has QQ bar-like quantum structures. So I have like 2 quark and anti-quark. So think about it like a quark model version of the rho with, let's say a gamma mu here. And I can construct different topologies by introducing, Wilson lines or covariant, any products of covariant derivatives. And so I have a long list of these operators I can do. And I can do this with like light anti-light and strange anti-strange, many operators, right? Then let me construct operators that look like 2 pions. And these are different because what I do in practice is that I grab 1 pion and I give it some definite momentum. And then another pion, and I give that one another definite momentum. They could be, with 0 total momentum or not. And these guys are Fourier transforms of operators that are local in space. And so this is an average over all my lattice. This is an average over all my lattice. And so these guys are, sampling the space very differently. So they're very different types of operators. And then we can construct with, operators with KK bar, and, we can give each one of these different momenta, right? And so we have a large list of operators. So here I'm showing you a calculation with something in the order of 27 operators. Okay. Step number 1. Before we talk about this plot, let me tell you a little bit of how this plot is generated. So instead, what we calculate are matrices of correlation functions, where we grab one of these operators, one of these 27 operators, and we put it at the source, and then we grab another one of these 27 operators, and we put it at the sink. And so we have a 27 by 27 correlation matrix. And all of these, using the spectral decomposition, will give me access to the same spectrum, but different coefficients, different overlaps, right? And these depend on the operators. And so the thing that you can do is then construct a matrix of these guys, and then you can use what is called the generalized eigenvalue problem, which basically amounts to a time-dependent eigenvalue problem. And those eigenvalues are going to be related to the spectrum at the asymptotically large time region. Okay. So that's the gist. But we can do this now that we've determined this correlation matrices for like 27 by 27. We can prune our correlation matrix and look at what happens to the eigenvalues that we obtain for smaller and smaller sets, right? We can't go bigger than 27 unless we do a new set of calculations, but we can definitely go for less, right? And so let's look at that. This is what the spectrum looks like if I use all of my operators. So here's 27 operators, and I have all these energy levels in some units that are lattice units. That doesn't matter for now, okay? So these tiny little points with error bars, these are the honest-to-God error bars, okay? Now let's do a crazy thing, which is only keep the pi operators. Well, I get this fat guys with like big error bars, right? These guys over here. If I include the KK bar, all of a sudden a new state appears. So I was missing this state from here. Okay. Now let me do something else crazy, which is remove all the pi, all the multi-particle operators and just keep the local ones. And I get a different state. And this is, it seems statistically consistent with this, sure, but all the other states are missing. That should give you pause. And there's many operators here. What I should have said, here's a little histogram. Here there's 3 operators, here's a 4, there's, 20 something, 27 minus 4, you can do the math. And I still miss all these states. That should be really, really concerning, right? Now I include pi and q and these q and I get some new states, but I'm missing this one that was here. Now I include everything, and then all of a sudden this state appears, and then I have all these other ones. So the spectrum should not be dependent on the operators that I use. But if you believe this plot, which I'm giving you a little bit to believe, but maybe not everything, that would tell you that the spectrum seems to be very, very sensitive on the operators that I use. And that's highly problematic and highly concerning. So it should, at least this should give you pause. But, let's say that that this is a final answer. Now you should ask me as good scientists, how do I trust the spectrum? Or at least how do I sleep at night? Saying this is like the honest to God QC spectrum in a tiny little box, how do I rest assured that I'm not doing just nonsense? And the answer to this is using finite volume formalism. This is the answer to this. I can describe these using some finite volume formalism, which is non-perturbative. Okay, any questions about that before I start diving into scattering theory? Yeah.
Finite volume formalism tells you that those 27 operators are okay, or I don't understand.
No, it's going to tell you something softer, which is I can describe all these continuously and many more spectra globally using one function, which is the infinite volume scattering amplitude, and that infinite volume scattering amplitude satisfies unitarity and analyticity. So it's not a proof, but it gives you at least some statistical confidence that this is not trivially related to one, that these are all well described by one underlying function, and that satisfies, at least unitarity and analyticity.
So if you change operators, you should find the same.
Yeah, we also did the obviously crazy thing, which is look at the formulas and using these spectra, and we get terrible chi-squares, as well as using this one. Yeah, unfortunately, I don't have plots here, but I can share them later. Yeah.
I'm not sure what you mean of the upper states, because you have 2-point function, you'll always have some excited states, right?
Oh yeah. There's many more states. I just didn't show them here.
Okay, so
I don't know what I said.
Pi bar gamma psi, that column.
Yeah, there's there's 27 operators, which means that I get something in the order of 27. There's 24 operators here, which means I get in the order of 24 total states. They're just really high energy. I'm just missing these states. Yeah. Okay, so what I'm going to tell you is that basically there's formalism that one could drive that is non-perturbative to relate finite volume spectra to infinite volume scattering amplitudes. And then these infinite volume scattering amplitudes can then be used to scan for resonances and bound states, and we can test principles of unitarity and analyticity on them. And so the key point is that we can do all this non-perturbative, or at least using all orders perturbation theory, which is the best thing that we have. So to describe this, I figured I would give you a little sketch on how to think about scattering theory for simple 2-particle systems before we go into the finite volume world, which is more obscure. And so the goal in here is to study 2-particle scattering amplitude for simple elastic region. For simplicity, we can generalize this. But what we want to do is really isolate all the kinematic singularities of the scattering amplitude, so that are infrared singularities. And these singularities are obtained from intermediate particles going on shell. And because the only things that can go on shell in QCD are hadrons, these are associated with hadrons going on shell. Quarks can't go on shell, right? And so here's my complex plane for the Mendelssohn variable S for this function. And so, experimentalists and us, we like to live in this axis, but we're theorists, well, I'm a theorist. I don't want to generalize. But, we can think of these functions off into a complex plane and describe them in terms of analytic structure and their singularities. And so in the complex plane in S, right, here's our minimal threshold. I'm gonna assume all the particles are identical and have the same mass and have spin, no zero, no spin. And so here's the first threshold associated with two particles being produced. Below, I can have a bound state and there's a pole on the real axis, and we're all poles on the real axis below thresholds. There can't be poles off into the complex plane that violates causality. And there can't be poles above here because that violates unitarity. I'd be happy to talk about all those things. But what we want to do is constrain the scattering amplitude in this region where experiments take place, where you can have two particles scattering onto each other. I guess the projector doesn't like it when I touch the screen. Is that what happened? Oh, it's on my side. It's my computer. My computer doesn't like it. There we go. Okay, so let's study the analytic properties of this function by just isolating all possible singularities. And so in general, scattering amplitudes satisfy integral equations. That's just always true. It's just a matter of finding what the integral equation is. The integral equation for this can be written in the simple form. And this is the integral equation for the off-shell amplitude, meaning these guys are not on shell. We can put them on shell at the end, okay? And I'm gonna be agnostic. I'm not gonna assume any underlying form for the underlying theory of QC at low energies. And so that means that, this object is an non-perturbative object, is a kernel, is what people describe as a beta subbeta kernel, and it can have contact terms, T-channel exchanges of all sorts. It can have three particle cuts. All of these are smooth functions. These are non-singular functions in this region. Three particle cuts can appear over here. Exchanges can be relevant singularities below threshold, but they can't be singularities above threshold. And so this function, I don't know what it is, but I know that it's purely real and smooth, okay? And so the only place where there can be singularities and be imaginary parts is in this two particle loop. And here I put little bubbles to suggest that these guys are fully dressed. But I'm gonna assume the residues are equal to 1 at the poles, and if not, that gets absorbed into what I define by the kernels. And so now that I have this, I can look at this simple loop, which is just two propagators. There's a kernel for the left-hand side. There's this off-shell amplitude for the right-hand side. And then I can isolate the singular part using Kukovsky rules, because the singular parts come from intermediate particles going on shell. And so one of these guys can be put on shell that kills one of the integrals. The rest is a smooth function, which I can isolate, saying that's the principal value piece of that integral. And then I have a remaining delta function thanks to Kukovsky. And then after a little bit of algebra, I'll leave this as homework. You just get that this whole thing is equal to the kernel, which has been partly placed on shell on the right-hand side, the amplitude, which has been partly placed on shell on the left-hand side, and then a phase space factor. And that's it. And you can just evaluate this. This phase space factor is proportional to the on-shell momenta of the two particles. And then, geometry, energies, yada, yada, yada. But the important thing is that P is equal to a square root of S. And this is very important. I mean, I didn't write it exactly, but like P is equal to the on-shell relative momenta, which is S over 4 minus S threshold over 4. And then S threshold is equal to 4m squared, and so this is equal to this. And the key point is that this has a branch point when S, the branch point of this, so it has a branch cut, and the branch point is equal to a threshold, right? So equal to a threshold. So this has a branch point at threshold. You can show that this cut has to be aligned towards the right. In complex analysis, that you can move these guys around as you wish. This guy you can't move around. This one is fixed by physics. And so this is it. That's the only cut. That's the only source of imaginary part in discontinuities of the whole amplitude in this region. After a little bit of massaging, you can show that this whole thing can be written in terms of some pure real function. Let's call it the K matrix, because why not? And then this satisfies now, this integral equation can then be written in terms of an algebraic equation for the on-shell amplitude because I put it on shell here, and now it's an algebraic equation in terms of the K matrix. And so this object comes from basically grabbing all the possible diagrams, replacing them with the principal value prescription, and that's what the K matrix is. And then after a little bit of massaging, you can then solve this algebraic equation, right? It's just a, one line of equation. And after placing everything on shell, and you get that the scattering amplitude is proportional to the inverse of the K matrix minus this I rho. And this rho is that branch cut that we showed, and it has to be diagonal because angular momentum is this is a matrix, but it's diagonal over all the degrees of freedom. And so because angular momentum is a good quantum number in the infinite volume. And what else do I want to say? You can relate this using, this is basically what we just derived. You can show that this satisfies the optical theorem by taking the imaginary part of this and remembering that K is equal to a real function. And then you can use unitarity, which relates S to M, and then that gives you a relationship between K and the scattering phase shift, right? Unitarity for a single channel tells you that S has to be equal to e to the 2is. But 2I delta, sorry, where delta is a phase shift. So unitarity takes you very far, but it doesn't tell you what this phase shift is, right? This is the only unknown, right? What we've done is constrain the scattering amplitude, which is a complex function singular, down to constraining that we constrain the singular part and the imaginary part, but we don't know what the real part is. And so you can imagine the scattering theory, well, all we want to do is obtain what this function is purely real function is from experiment or lattice QCD. And so that's what we can hope to constrain. Okay? Any questions at this point? Yeah. Oh, sorry, you wanted to change the page. Sorry. Say that again.
The second one, that propagator is not rest.
This one right here
Yes, yes,
is not what?
rest propagator.
No, I mean, what I said is that in the on-shell limit, the dress propagator will have a residue of 1. But it is a dress propagator. I mean, it's a dress propagator, which, in the limit that I take it to be on-shell, then it will give me 1. And then the rest of the pole would just be the physical mass. All right, so what I had is that in the on-shell limit, this becomes where M is a physical mass. Yeah, good. Any other question? Okay. So you can use these techniques to go to higher energies and also go towards the left-hand side. There can be left-hand cuts. Going to higher energies, you can now allow for 3 particles to go on shell. And basically, we're working in all directions, both towards the left-hand cuts and also towards the right-hand higher energies. And you can use these principles of all orders perturbation theory to put constraints on the analytic structure of these amplitudes exactly. But there's always going to be some unknown function that needs to be constrained, and the goal is to constrain these functions from the lattice. And so that brings me to finite volume physics. And so now let's think about there's a connection between the spectrum and a box to the infinite volume scattering amplitude. And so let's sketch this out. Yesterday, I already told you that the spectrum of a single particle is always exponentially close to that of a to its mass in infinite volume up to corrections that scale like this. And so in everything that I will consider, I will be thinking that the volume is so big, it's sufficiently big that n pi L is much bigger than 1. So you can imagine that n pi L has to be in the order of 4 or bigger for me to safely ignore these exponential corrections. And so that means that at least single particle states fit on a box just perfectly fine. And then all the other errors that I make are associated with multi-particle effects. And those parts we can isolate exactly. So here, now if I look at the landscape of 2-point correlation functions in energy, the poles of these functions are going to give me the spectrum in a box. And the spectrum in a box is completely discrete. Okay, because I've introduced some infrared cutoff. And these are gonna be purely real on the real axis. And so that means that in a finite volume, there's no continuum. Okay, you only have a complete set of, you only have discrete states. Furthermore, I don't have asymptotic states. Because if I try to pull the particles apart, they either interact when they're either interacting with themselves or they're interacting with the boundaries or their mirror images. And so there's no notion of scattering on a lattice. You just simply can't do it. And so that is the only way to do this, is by looking, what we want to do is drive an equation that the spectrum in a box must satisfy. And we'll do it in the same region that we consider the scattering amplitude, which is this region. And what we can observe, what we want to do is isolate all the power law finite volume effects. I will ignore exponential errors. I will only keep power law effects. And the observation is that these come from intermediate particles that can go on shell and sample the boundaries of your system. And so basically the tools are very similar. And so let me look at an object that is a little bit funny to think about, which is the finite volume analog of the scattering amplitude. It's funny because I just told you scattering is impossible in a finite volume, but you know, we can still define this object mathematically. And again, this satisfies an integral equation. In this case, I'll have to sum over momenta, the spatial momenta, and the momenta have to be discrete. And they satisfy, if I have periodic boundary conditions, they have to be, they satisfy that K is equal to 2 pi over L times an integer triplet nx, ny, and c, where each one of these is an integer. Okay, and they can go from, you know, each one of them from negative infinity to infinity. And so the equation that this satisfies is very similar to what we had before, except now the loops are in a finite volume. And so this kernel, which includes contact term, exchanges, etc., is also in a finite volume. But the key point is that these guys can't go on shell. Neither of these guys can go on shell in this kinematic region. And so the difference between the finite volume analog of this and the infinite volume is exponentially suppressed. And I started giving a sketch of this to folks yesterday in the discussion session. We can discuss this further if you want. But so that means that the only object associated with finite volume effects is this one, the only one that has power law effects. And so then we can do this like very magical identity, which is this is equal to itself plus and minus the same thing. Okay, so not super magical. So this is an infinite volume analog of this. Okay, so V stands for volume, right? And so I just grab the infinite volume and I added and subtracted. This is some unknown function. I don't claim to understand what this is. Previously, we actually just isolated the singularities. In general, I don't know what it is. But what you can then show is that this thing is given only by the intermediate. The difference between these things is exponentially small, except for one term, which is given by the poles of these two guys. And so it's given by and I just write it here explicitly. So this dash thing, we give it explicitly, which is basically a function that places these two guys on shell. So the kernel on the left-hand side, the finite volume analog on the right-hand side, and then some geometric function, which is basically just a finite volume analog of this row phase space function that we discussed before. It's a little more complicated because it's really the sum minus an integral of some function. And also angular momentum is not a good quantum number in a finite volume. And so this mixes different angular momentum. So L here is a angular momentum of, let's say, some incoming state. M is a symmetric component. And here L prime and M prime don't have to be equal to L and M because you're summing over momentum instead of integrating. And so this function is some kinematic function. Is, you know, it depends only on on-shell kinematics, but it's a non-diagonal function. But nevertheless, you can determine this exactly. And so after a little bit of massaging, you know, following very similar steps before, you can show that this finite volume correlator, which I made as a little square, can be related to the infinite volume amplitude, which is in a circle. And after a little bit of work, you can show it's just equal to M times this thing 1 plus Fm. And so this in general can diverge. That's the key point. So this thing can diverge and it must diverge because we know the finite volume correlators are sums over poles. And so this has to have poles. But these are matrices, right? And so the locations of these matrices that diverge are given by the determinant of this function. I could have written it, you know, as like determinant of 1 plus mf or whatever. There's many ways of writing these things. They're all equivalent. And so the determinant is given by, the spectrum is given by this determining condition. So there's a quantization condition that the spectrum must satisfy. What else I want to say? Let me say a few more comments and then I'll ask for questions. So this equation, right, relates the spectrum that goes into this function. This function is known. This m in general we don't know, but it can give us a constraint that the amplitude must satisfy. So p is the momentum in the finite volume, L is the volume, and p squared is the Mandelstam variable s that is related to p, obviously, in an obvious way. And so this gives me a constraint that the amplitude must satisfy. F is a function that we know. This equation is exact up to exponentially small fractions. You're always making those kinds of errors. We're fine with that. This is a mapping. This is not an extrapolation, right? This is a relationship between the finite volume spectrum and infinite volume amplitudes exactly. And so it doesn't require an extrapolation. It's not one-to-one, so it's not a one-to-one mapping. It's a one-to-many mapping because angular momentum is not a good quantum number. But for moderate energies, low partial waves saturate the amplitude, so we can use partial wave expansion. And there's a function that we know in general. We know it for arbitrary boosts, etc. And we know the spectrum will be different at different boosts because if you boost the system in some direction, it will Lorentz contract, and we don't have Lorentz symmetry in a finite volume. Those are all the claims about this equation. Okay, are there any questions about this so far? It can't be that it was that clear. So. I'll just awkwardly drink water until somebody asks a question. Breaks my heart, but there's no questions, but fine. We can go on. Okay, so extending these ideas for, larger number of particles, hard, but it can be done. We are doing it. You can also extend these ideas downward where all the dragons lie associated with Leffin cuts. It's also hard, but we're doing it. It's not super hard. It can be done. If I can do it, you guys can do it. Let's put it that way. And so that was basically it. That's all the formal stuff. So from now on, I'm just going to show you plots. Okay. And so let's go into actual lattice calculations. So basically what I'm going to show you is the calculation of two pions with increasingly lower angular isospin, which just basically shows the power of these tools, and that has been applied to many systems. And all the plots kind of look the same. So let's walk over one of them, and then afterwards I'll kind of skip over them a little bit quickly. So here is calculations for a system at rest. So what I'm showing you above is the momentum of the system, the total momentum of the system in units of 2 pi over L. Okay, so I'm just showing you the boost factor. Okay, so 0, 0, 0, so it's unboosted. 0, 0, 1, we boosted it along the z-axis. 0, 1, 1, boosted it along the y-z axis. 0, you get the idea, right? And we've done the calculations for two different volumes. One that is 20 cubed in lattice units and one that is 24 cubed in lattice units. And we've repeated that for all the boosts. Each of the boosts, we determine many energy levels, and we scale the energies by the pion mass. Remember, we don't have dimensionful quantities on the lattice. We only get ratios of things. This is for a pion mass that is approximately 400 MeV, and the isospin of the pions is 2. So this really means like 2 pi pluses, okay? And so we get many energy levels, and there are these little tiny black dots, which are probably hard to see from the far. And so anyways, you get many energy levels. And then what we can do is use this formalism, right, that we just talked about. And this gives me a constraint for the amplitude from the spectrum. And so we can literally, and before I show you the next thing that we do, we can write M using unitarity in terms of the scattering phase shift. And so the interesting part is P cotangent delta. And then lastly, we'll take the inverse of picotangent delta to keep you on your toes, okay? No good reason. Well, basically this thing would be flat and that flat value will be related to the scattering length. If it's flat, it doesn't have to be flat, it's just flat in this system because it's super boring. And so literally what this equation tells you is I grab one energy level, you shove it into this function, and then that gives me a value for this function, which gives me a constraint on the scattering amplitude, which is this constraint at that same energy. Okay, so it gives me a constraint of the scattering amplitude, in particular the picotangent delta or the inverse of it at that given energy, right? And you repeat this for a bunch of, energy levels here, a different boost, different volumes, and they can all be related to one function, which we argued this function had to be purely real due to unitarity and have no other singularities. And, I can't convince you that this is not a singular function, but it looks pretty, that is a non-singular function, but it looks pretty non-singular, right? And so this is how I can sleep at night. Basically, you put some mathematical constraints and you get some function, and statistically speaking, this is just a constant. It doesn't look like anything else. Super boring. Okay. Any questions about this before we do more interesting stuff?
Finger edge shift can describe several forces.
Yeah, because the two particle scattering amplitude really there's a function of p squared. I made a little typo, but it's a Lorentz scalar, and so that is the same is frame independent. This right here is frame dependent because we don't have Lorentz symmetry in a finite volume, and so the spectrum across different boosts is different. There's nothing that assures that they're going to be the same because you've broken Lorentz symmetry. But we know how to relate them, all of them, to some Lorentz scalar infinite volume function. And so all these, you can see, so the open circles are from the 20 cube lattice, the closed circles or the closed symbols are from the 24 cube. And depending on the symbol, it corresponds to different boosts. And they're all related to the same infinite volume quantity. Really what we fit is a spectrum, and you see the fits in these like little lines that are orange, and they're just basically crossing. The chi-squared is in the order of 1 or something like that. Yeah.
Right. I mean, the mass of the ion is more than the experimental one, right?
Yeah.
But it's because it's more convenient because you get ML much greater than 1.
Correct.
And you take ratios. So it's not how much the result is dependent.
Super independent. Super independent. Everything it runs. I think I'll give you an example in a second. Where like basically the quark mass dependence is very steep. Yeah, everything depends on the quark mass. And it depends on like the questions that you're trying to ask. So let's say the question that you're trying to ask is simple. Is there a state there or not? That is a binary question that should have an answer that is quark mass independent. What could happen, and I didn't discuss this well enough, this will be relevant in a second, is how do I define resonances, right? I told you that you can't have, or I think I said this, here, I'll test your knowledge. So I have the Mandelson variable S, right? And so I can map out the analytic structure of the two particle scattering amplitude, and I just told you there's a branch cut right here, right? So where do bound states lie in this complex plane? This is something I said like 10 minutes ago, so 5 minutes ago. I like to say there's no wrong answer to make you feel good, but there's no shame in saying the wrong thing. Let's put it that way. Also, it's not a rhetorical question. Like it is meant for you guys. So we're do bound states. So here's my threshold saying 2 pions right here. If I had a bound state, where would the bound state lie? Lots of people are mumbling the answer. Yeah, what's up?
To the left on the real line.
Yeah, to the left on the real line. There we go. It'd be bound, so it'd be below threshold. It can't decay, right? To anything, and so it has to be here. Good. Okay. I said that they can't be complex value poles. Does anybody remember why? I said it really quickly. Okay, I'll forgive that one. There can't be any complex value poles because of causality. Because if you do Fourier transform with these, you would get correlation functions in time that have the wrong time behavior. So you can't have that. That's not allowed. I said that you can't have poles on the real axis because of unitarity. And unitarity told us that the imaginary part of the scattering amplitude is equal to m star rho m. And so if I had a pole along the real axis, this means like an honest to gut pole, this would mean that the scattering amplitude would diverge like S minus S0, where S0 is my pole. And so the right-hand side is certainly not zero. So the right-hand side would be order 1 over S minus S0 squared, right? And the left-hand side, depending on, whether these things are real or not, it would be either 0 or, at best, order 1 over S minus S0. And so this is diverging twice as fast as this, or even more. And so this is prohibited by unitarity. So you can't have poles here. So if anybody tells you that they found a state that is above threshold and is because they're associated with some peak or something like that, that can't be a state. Okay. So where are resonances? They can't be complex valued in the sheets. And they can't be on the real axis. So where can they go? The imaginary axis, but it can't be on this physical sheet, right? Because I just told you that violates causality. So the take-home message is that here we've introduced a square root singularity, right? So this square root goes like S minus S threshold. That means that this is a two-sheeted object. And the physical sheet is where we all live. And what happens is that if you have a toy model where you have a pole here, and then you allow it to couple to multi-particle states, then this guy is gonna move down off into the second sheet. And there's a gap here, right? That's what you have a cut. So there's a multi-sheeted thing, then that moves here. And what you see experimentally is a projection of this nearby pole. That's what you see this thing. Projected. You don't see a pole would be diverging, right? You see a nice little bump because you have a nearby pole. And the gap here is proportional to the decay width. And the value of it is proportional to its mass. Okay? So that's resonance physics in a nutshell. Now let's look at a resonance. Okay, so we went from isospin 2, maybe I should ask, are there any questions about all that stuff? I kind of went quickly through it, but basically, the answer is complex analysis is useful and here too. Okay, so let's go to isospin 1. This is where the rho would live, okay? Here we determine many energy levels. Here they are for different boosts, different volumes. I'm not gonna bother to zoom in. It's the same story as before. And we've done calculations for 2 different quark masses. In fact, multiple quark masses, and I'll show you the result of that in a second. So here the pions are roughly 400 MeVs, the same as the other world that I just showed you. And then here in red is approximately 240 MeV. So it's a little lighter. And what do you see? Well, I can show you the scattering amplitude or peak cotangent delta or the phase shift. I'm showing you this time the phase shift. So the phase shift in this case goes from 0 to 90 for the 400 MeV, and it does this very sharply, right? And the distance that it takes to go through this basically is related to the width of the object, which is related to the width of the resonance, right? So this is a very narrow resonance because it goes in a very sharp rise in a very small energy region. Meanwhile, if we go to a lighter quark mass, the phase space for this guy to decay opens up, and so it becomes broader. In terms of complex analysis, it's moving further into the complex line. And so we can now scan, we can look at these functions in the complex plane and look for poles. after having done a global analysis and fitted them with these functions. So in this case, it's just two paraweakness. You can use whatever parameterizations you want. And then you do an extrapolation off into the complex plane. We don't have lattice data in the complex plane, just like we don't have experimental data in the complex plane. But mathematically, there's nothing that prohibits us from this. And so what's happening? At 700 MeV, this is a real axis, this is an imaginary axis of energy. At 700 MeV, the rho is bound. It's on the real axis. At 540, it's still bound. At 400, it starts to walk off into the complex plane. And then at 236, it moves off even further into the complex plane. We've done cargo extrapolations and we get this value. And then if you compare it to experiments, experiments over here. So it seems like these states, right? If we think about QCD as a more complicated, phase space than just like the God-given quark parameters, and we think of these functions in the parameter space of the quark masses, these states just evolve naturally, and they're connected, smoothly connected. If you think of them as poles in scattering amplitudes. So they walk off and, their widths are, open up with their phase space up to, couplings, and you can determine these couplings quite well. Okay. There's no questions about that. Let's go to the next channel. So we went from 2 to 1. Let's go to 0 in terms of isospin. So this is the quantum numbers of the vacuum. So let's look at 0 plus plus. This is a really fascinating sector because you have many open questions. So there's a sigma that lives there, which now is being described by the PDG as F0 500. For many years, people were debating as to whether this guy was even real. There's an F0 980, which has been hypothesized to be a molecule. There's possibly two blue ball candidates. I should have highlighted this is a possible blue ball candidate, the 1500 and the 1710. And so there's many interesting things to study here. This, whether this is a real or not comes down to the fact that this is very, very broad resonance off into the complex plane, and it decays 100% of the time to 2 pions. This guy is seen as hypothesized as a potential molecule because it's close to the kK-bar threshold, but again, it also decays to 2 pions. And so here the data on the lattice is much more complicated. You have many energy levels that we can constrain. They don't tell a very simple story. You have many open thresholds. So here's pi threshold, here's the kK-bar threshold, here's the eta threshold. This is a real mess to look at. And so the only way to get away from making any physics outcome out of this is using the kind of formulas that I showed you. There is one state here that you can kind of look at it and squint and say something about it, which is this low line state. This is again for the same 400 MeV world, which is a kind of a testing bed for all these ideas. And here we see that this guy seems to be a big object that has very large volume effects. So this is a box of 2 Fermi, 2.5 Fermi, 3 Fermi or so. And it seems to dramatically change with the volume, which suggests that this guy is probably a big fuzzy object, potentially a molecule. We don't know. But nevertheless, you can grab all these, there's no simple story in all this. And so let's just jump into the results. So you can do a global analysis of these. In this case, things get more complicated because you can have these determinants are no longer, it can't be written in a simple algebraic form. So you don't have like one-to-one correspondence with a spectrum, but you can do a global analysis by constraining amplitudes using parameterizations and minimizing those parameters given the lattice data. And then at the end of the day, what you end up getting is an amplitudes like this, where you have the pi to pi amplitude right here, weighted by the phase space. Then you have the kK-bar to kK-bar amplitude and the pi to kK-bar amplitude. These are super strongly coupled. There's a lot of dynamics going on here. And also we see evidence for the sigma. So this was the first evidence that the sigma appears in QCD. And then here's the F0 980, which appears as to be strongly coupled, coupling both to the kK-bar as well as the pi, just like an experiment. And basically what I want to leave you with, I'll leave you with a couple of new, things, basically just big broad messages in terms of what's being done. But then also I'll tell you about some things that are where this is being generalized. So these calculations now for simple 2-particle systems, including coupled channel systems, resonance with many resonances, are being done in the light sector as well as in the heavy sector. There's many calculations that are being done by my collaboration as well as others. So it's really an exciting, it's something that has been opened up in the last 5, 10 years at most. So it's very new avenue of research. The fuel body frontier, meaning what things are being done today, are trying to adopt this to the nuclear sector. The nuclear sector has proven to be a lot harder because there's heavy signal to noise problems. So even simple questions like, does the deuteron exist at heavy quark masses? It's very hard to pin down. People have been debating about this for many years now. It seems like the deuteron, so this is actual deuteron data right here. So there's 2 nucleon data where for the deuteron channel. And depending on the lattice framework that has been used, you will get phase shifts that look like this or like this. And depending on which one you trust, will tell you something very different about the nature of the deuteron. It seems like the latest data, which I didn't include here because it hasn't been published yet, points basically to this being the right answer. And this is the only one that used GVP, using many large operator bases. And so there's good evidence to believe this and maybe less to believe this. But I want to say is that if we want to study properties of light nuclei, this is still outstanding problems, and it could be beat down with more statistics, better algorithms, better techniques. But there's many exciting things to be done there. The next frontier, or correlatedly, is trying to start studying amplitudes where you don't have just resonances or bound states or multi-particle systems that are purely hadronic, but also incorporating electroweak probes. And this is something that some of my collaborators and I have been pushing. So I've been developing a lot of formalism a la what I showed you, and developing connections between what can be calculated on the lattice and infinite volume amplitudes. But to this day, only a handful of calculations have been done. This is the first one where a resonant electromagnetic process was performed, where we studied pi gamma star to pi pi as a function of energy and also as a function of virtuality. And this has now been extended to other states. But this is basically new novel for frontier. And the last one I'll mention is that these techniques have been super powerful for studying 2-particle systems. And so there's been a lot of push to extend these for 3-particle states, because most resonances and most states, most nuclei have not just 2 particles in them, but they have more. And so we've been trying to extend these ideas. The formalism has been proven to be formidable, and its implementation even more so. So in fact, to this day, there's only been one lattice calculation of a 3-particle scattering amplitude, which is the most boring channel possible, which is of 3 pi pluses. We're now actively working in other channels, but this has proven to be quite challenging. So it's still an exciting line of research, because we can in principle study observables that are experimentally inaccessible. So honestly, God, 3 particles come in, 3 particles come out, and we can scan this as a function of energy, but also as a function of the energy of the 2-particle subsystems. And here's the first lattice plot of a lattice calculation, where here we fix the total energy of the system, but we're scanning the 2-particle subsystems energy. And so you have this like kind of funny, interesting behavior. So I think this is all I wanted to cover the last 2 days. Just to recap, lattice QC does work. It's a remarkably powerful tool, and there's a great deal of investment going towards it, because it really is the only tool that we have at our disposal to non-perturbatively study 1/4 of all the forces that we know to be true. And the reason why it works is because of all the points that we discussed in the last 2 days, right? QC is kind of like a perfect match for lattice field theories. The limitations are really unclear. There's many things that can be done naively, straightforwardly, but there's even more that can be done in requiring much more sophisticated formalism and much more clever ideas. And there's really no clear limitations. The cutting edge in research is really, I couldn't have done it justice. At some point I debated giving you a broad survey of everything that is being done. That I thought wouldn't be as good, but basically there's been a lot of efforts in hydrostructure, PDFs, GPDs. I mean, GPDs are just starting, but also TMDs. There's a lot of work in some fundamental symmetry. Electroweak or weak matrix elements has been the bread and butter of lattice QC for a long time. It's not until recent that scattering has started to take place on the lattice, and this is because the formalism itself is much more complicated, but also the calculations themselves and the analysis is far more complicated than those of simple particle states. There's many other stuff that I couldn't really have been able to cover, finite temperature, finite density, weak decays, BSM searches. There's really a thriving community of lattice QCD out there. So I think that's all I got for you. So thank you so much for your attention.
We have time for questions if folks have some.
Why is the 3 pi plus the most boring 3-body channel?
So there's some good arguments. So it's first, the two particle system is very weakly coupled. So there's no resonances in the two particle sector. So 2 pi pluses, right? Just think about, so if you think about the system, I'll give you a counterexample that is more interesting. There's many examples that are more interesting, but if you grab 2 pi pluses, these guys, we have already studied them. We've seen them experimentally. There's no formation. There's no bound states or resonances here. And then also from chiral perturbation theory, there's, chiral symmetry tells you that this is a very weakly coupled system. So that's consistent with chiral perturbation theory. Chiral perturbation theory also suggests that this is very weakly interacting. And so in this case, in fact, it didn't show you, but this whole spectrum, all these energy levels, we can describe using just 3 parameters. This is in the order of 100 energy levels. We can describe it using 3 parameters: the pi mass, the 2 particle scattering length, and then some short distance 3 particle object, some K matrix of sorts. And the black points are the lattice data, and the orange bands is what we get if you get this 3-body contact interaction to be 0. And so there's evidence for there not being any 3-body force, which is what we expected from CAPT. And the reason why we wanted to do this calculation is to basically test our technology both on the computational side and the analysis front. There's many more interesting channels. I mean, the isoscalar channel is where the omega would appear. So the omega couples to the rho, which then decays. So to rho pi, and then the rho decays to pions. In the isospin 1 channel, you have the A1, and then this can couple to many channels. So this can couple. This is a beast. This can couple to rho and pi, but it can also couple to sigma pi, and then it can also couple to isospin 2 and the pion. And so it's a complicated object, but there's good motivation to study this. But it's a much more there's many channels open, and so this is a hard place to go first. And there's isospin 2. So 3 pions you can put in isospin 3, which we did, 2, 1, or 0. In isospin 2, there's nothing. The expectation is that there's no resonance there. But you still have a couple channel system where you can put the rho and the pion, which the rho indicates the 2 pion, or you can put 2 pions in isospin 2. So there's any channel. So this is a couple channel system, which this one wasn't. So any channel will be more interesting and more challenging than this one. That's why we decided to go for this one first, just to make sure that we're not kidding ourselves. Yeah, great question.
If not, we'll have a chance to think, and again, we'll have an evening discussion at 7:30. So let's thank you all again. Now, let's take half an hour, and we'll start at 40 after with the tutorial then. Courtney?